Suppose we looked at the problem that we actually already kind of looked at, which was keys on a lanyard. Suppose we lift them to parallel with the ground and release them. They swing down, this we know. How fast are they going at the bottom?
No, zero.
Bottom?
Yeah, because it's not a switch direction. So it's zero.
Vertically, yeah, you're right. But they are still moving horizontally, right?
Yeah.
Yeah, so they have some speed at the bottom. And our question is, what speed is that? All right. What do we have to attach to this question? There's very little that's given to us. The only thing we're told is that the lanyard is 45 centimeters long.
Mhm.
That's it.
Mhm.
We don't know the mass. We don't know anything else. We do know we do know G. Yeah. So I start reaching for things to say. Up until now, the thing to say has been Newton's second law, which makes me think that I want to draw a free body diagram. Even if I start thinking about energy and work, I'm still going to need to know what forces are acting in order to talk about how much work they're doing. So a free body diagram didn't really, it's not going to hurt everybody. Suppose we pick some point along the way. You're right that there is gravity. What else?
Tension of the
Tension in the lanyard, absolutely. We know that that exists because if it didn't, it would just fall straight down. Since it doesn't do that, there must be another force. And the only place to get one is the tension. Okay. And I'm starting to panic. Because if I had drawn a different free body diagram, those angles would have been different. Yeah. And the worst part of it is the acceleration changes direction constantly. Because gravity is what it is, but the tension changes direction constantly. So the sum of the two of them also has to change direction constantly. This is a situation in which we have an explicitly non-constant acceleration. I actively want to avoid kinematics. Our kinematics was built for constant acceleration, right? We've got those 5 equations. None of them apply here.
I only.
If they did, we would have to do calculus because we've got a thing that is constantly changing. It is not very well suited for Newton's second law or kinematics. The other thing I have is energy.
So wait, if we did do calculus, could you take like the river?
Or maybe integrate, but yeah. Gravity is acting, so that makes me think about potential energy. Tension is acting, and it is a non-conservative force. I'm asked about the velocity at some point. That makes me think about kinetic energy. I think the work energy theorem is a really good choice for this, especially because none of this is a vector. I don't care about the direction. When we talk about work, the work done by gravity is the same to get from this height to this height, no matter whether we're going in a curve or a straight line or just vertically down or whatever. It's path independent. This is great.
But, alright, so where is gravity in this then?
Here. We agreed that we could keep the books, maintain our balance sheet, right? For gravity,
Oh,
either as work done or as potential energy stored,
oh,
not both.
okay,
If you wanted to talk about the work done by gravity, then I'd put it back over here and just talk about the net work done. If we want to talk about potential energy, then I unpack it and I put it over here.
okay.
We've got to account for it either way, right? Like the bank's going to tell you how much money you have. We just need to, whether you want to put it in column A or column B. Okay. I'm a little bit nervous about this. The sum of all the non-conservative work. There's only one force doing non-conservative work, and that's tension. The work done by tension, which by definition has a directional thing, right? It's a dot product. This should be the force of tension dot the displacement. But here's,
The difference of two, but since there isn't.
we are going to need the angle between the force of tension and the displacement, and that's the key to the whole thing.
So you're saying work of tension, meaning that you're only going to be referring to the tension, the force,
Mhm.
the tension force.
Mhm.
Okay.
The only non-conservative force to worry about is tension. So that's the only one I'm going to worry about. The great thing about tension in this situation, no matter where we are on this circular path, the tension points from the circle to the connection point, to where I'm holding the lanyard. Tension is directed radially along the radius of this circle.
In this case, tension is not conservative
Because tension is always not conservative. If I try to do some work by pulling with a thing, it's going to move in the direction I pull no matter what.
where is it from?
If it's stretchy,
Yeah.
then that's a different thing, and that's elastic. If we're just going to communicate a force with a string or a cord or a cable that doesn't stretch, non-conservative. Our displacement is along a circular path, right? We're following this direction. What can you tell me about the geometrical orientation of a tangent and a radius?
Wait, sorry.
The table is tangent to the circle right now.
It touches the point.
If we draw a radius to the point of tangency, what's the angle between that radius and the tangent? 90 degrees. They're perpendicular. Every radius we draw is perpendicular to the circular path. A radius is always perpendicular to a tangent. So the whole way along, the tension is radial and the displacement is tangential. The angle between those two things will always be 90 degrees.
What? Oh. So every ray is perpendicular to a tangent line.
Mhm.
So the displacement is tangential.
Yes,
Okay.
I should write that. That's a good call. And the cosine of 90 degrees is close.
So 0.
That's the other thing.
Wait,
X or Y?
oh, yeah, never mind.
Cosine is X.
Yeah.
Gosh.
Cosine of 90 is 0. In a circular path,
That's a pretty good circle.
tension does not do any work. Never. All it can do is redirect the energy we have. It cannot change the energy we have. If we would speed up, it's not because of tension, it's because of gravity.
But why would it? Okay, so if gravity is the same thing all the time, how is it able to speed up in the first place?
Well, because there's nothing canceling it. Gravity pulls down, the tension, if it needed to, would act to the right. So there's nothing to stop gravity from pulling this thing down.
Uh-huh.
As soon as it moves a little bit, then there's some tension which just kind of pulls us into circle,
Instead
but
of
it
going
can't
forever.
change how fast we're going instead of just falling, right?
Okay.
The change in kinetic energy. We end with something, and we started with 0 because we released the keys from rest. I just need a way to talk about the change in the gravitational potential energy. And then I'm golden. So the change in the gravitational potential energy, because of the way we defined potential energy, is the negative of the work done by gravity.
So,
If we're going to make a deposit into savings, we had to withdraw from checking. That minus sign, it's got to be there. The work done by gravity, I know how to calculate that. Force of gravity, not the displacement. Now,
so
the important part of the dot product is that it only cares about the vertical displacement. We're going to take the displacement we have, which is some kind of wacky circle, and slam it onto the gravity's number line, which is vertical. All we care about is the vertical displacement.
so from 45 to 90. No, from that to
Not even angular, just how far. How far is it vertically from here to here? Because that's what happened. It doesn't matter whether we go up a ramp at 30 degrees or just lift 2 meters. The point is, we moved 2 meters up or down. So how far up or down did we go? 45 centimeters. Absolutely. Negative mg 5 centimeters. Because that's the length of the string.
Mhm.
like to give you a rule that we can use going forward. The change in gravitational potential energy only cares about our height. Did we go up? Then delta H is positive. Did we go down? Then delta H is negative. That negative 45 degrees is right here. Negative 45 degrees.
I was about to say, what about left and right, but that would be friction.
That there's gravity doesn't care about that.
Yeah,
Gravity only wants the vertical part of our motion. Only the height. And this, I said up or down, not in the positive Y or the negative Y. This is up or down, never mind your coordinate system. Because it all has to do with the orientation between gravity and our displacement. Doesn't matter whether you draw your coordinate system one way or the other. If we're moving down, even if you call it that positive, that's the same direction as gravity, and that's what I care about. The dot product cares what's in the same direction. The minus sign has to be there because of debits and credits. And we can fold that minus sign in to delta H if we talk about up and down. Gravity,
going in the same direction.
well, yeah, essentially.
Okay,
Gravity only cares about whether we are moving closer to the surface of the Earth. If we are, then delta H is negative. Because we moved down.
cool.
No matter how you labeled your coordinate system,
So if
we
you're
moved
going,
closer in the direction gravity wants us to.
then it's negative?
Then delta PE is negative because delta H
Oh.
is negative.
Oh, okay.
Yep. That's 0 and p squared. Plus mg delta h. Same story here. Plus mg delta h. Same story. Now, what we wanted the speed. All right, so let's solve for that. I don't know the mass. Is that a problem?
Find it.
It is not a problem, and I can't find it.
Can't
But it's not a problem
Can't find
because
Mass? you said? Oh, because you can divide it.
we can cancel it.
You have to divide it.
Let's multiply by 2. And let's take a square root. Are we taking the square root of a negative number?
So right there, yeah.
Oh, but it's also negative,
But delta H is negative.
so it's positive.
So we're safe. We don't need to imagine any answers. As much fun as the square root of -1 is, we don't need to worry with it. -2 times 9.8 times negative 0.45 meters. And we're done. Square root of 2, 9.8, 145. Just about 3 meters per second. And we can do that all we were given was the length of the string. And that's the power of these energy methods. We can paper over all this directional bullshit because work collapses everything to number lines. Questions, comments, concerns?